乱讲话都被录进去，太太录了。
没关系，我心里正确。
我原本想说可以录音就好。说他上课，然后说可以去开台，不知道怎样。对，借一下，借一下，我借。上次我就开始笑。
Okay, so let's start today's class. So due to the COVID situation, so we will still have in-person class until the university has any announcement. But I will record the in-person lecture, so in case someone cannot attend the class. So, but actually I record every class since the semester starts. So if you need this video, I'm happy to provide it. Okay, so if you need this for review, that's fine. Okay. So the principle is, if you think you don't want to come to school or come to class, feel free to just not go to the class. Okay, and also, but the quality for the video maybe is not good as the in-person class because it's just record the screen. Okay. Okay, so today I have uploaded the slide to the my website. So today we will discuss synthetic control methods. I think some of your term paper might use this method. Okay, so synthetic control method. So the main idea, so let me check. So these methods you can consider is kind of like improvement of the difference in difference, but they actually deal with different issue apply to a different situation. So this method can help you to estimate the causal effect. And it's a new method, and just start from like 10 years ago, become popular in the social science. And it's quite popular in social science due to the following reasons. The first reason is it can deal with some issue that some other causal inference method cannot really deal with. Is it can evaluate the treatment effect on the aggregate level outcome. Just if you just have very few treated units, for example, just one country get treated, and you can evaluate the causal effect on that country, okay, or some county level or city level. So it's basically focused on the aggregate level outcomes instead of individual level outcomes. And they use the data-driven procedure to construct the suitable counterfactual for the treated unit. Okay, I will mention how they construct. And use a small number of non-treated units to create this counterfactual for the treatment group. So that's the principle. So it can use very few data points, just one treated unit, and small number non-treated units. It can conduct the causal inference. So it's especially suitable for the aggregate level outcome, country level, city level, county level. And the main idea is they use a very long panel data to build the weighted average of non-traded units and use this weighted average to construct the counterfactual outcome for the traded units. And we call this weighted average non-traded units so-called the synthetic units. And this synthetic unit, how they choose the weight, I mean, how they choose which control unit get how much weight. It's based on whether this set of weight can help this synthetic unit to produce the best, the most closest characteristic of treated units in the pre-treatment period. Okay, so what does this mean? I will discuss later. And then if we can find such weighting, we can use these things, compare the outcome of synthetic units and the outcome of the treated units, compare their difference after the treatment happened. It can give us the causal effect. Okay, so here I use the classical example to demonstrate what does this mean. This is the author want to understand how does the anti-tobacco law passed in 1989 in California. How does this affect the California's cigarette consumption? Okay, so basically this policy tried to persuade people to not smoking. And how does this affect cigarette consumption in California? And in the very beginning, you might think I just used other states in US as the control group and conduct the difference. But the difference, you need a common trend assumption. And sometimes it fails. For example, this example, you can find the California cigarette consumption is this trend before treatment happened. But the rest of US is this. So this trend is not really parallel. And they are not very similar. So we cannot say this gap is represent the policy effect. The gap between the rest of US, the simple average of the control units and California, this gap cannot really represent the policy effect because the gap already exists before the treatment happened. Okay. So the synthetic control is doing that is we choose the weight, some weight, assign some weighting to the rest of US. So instead of using the simple average, we use weighted average. So simple average is every state in the control group receive the same weight. They just average over the data. And the outcome just very different. But maybe New York or Alaska, their cigarette consumption is more similar to California. So we just give them higher weight. And the weight, how we choose the weight is we want to choose the weight that can help us to match the outcome before treatment happened as similar as California's outcome. And if we can find such weight, we just use that weight to construct the control group. That's so-called synthetic California. And for their example, they actually find such weight. So this weight could be 20% New York, 50% Alaska, or 30% Utah. And other states, other 40 states, just 0. And it matched the California very well before treatment happened. And then, if we can find such weight, so it's arguably say anything difference after treatment occurs can represent the causal effect. So we can get the causal effect for 1990, 1995. So evaluate every year how does this policy affect the cigarette consumption in every year. Okay, so that's the basic idea of the synthetic control. So instead of using the simple average, we cannot find a good control unit. We use the weighted average. And how we choose that weight is based on the data-driven approach. Try to minimize the difference in the outcome between the treated unit and these synthetic units. Okay. So any question for this? Okay. So synthetic control method built on the setting of the standard difference, but they have following change. One change is they use the data-driven approach to construct the counterfactual using the control groups. Okay, for the treatment group, to using the control group. And so it's data-driven. So it's not can decide by the researcher. You just put all the control groups, control units in the data, and the algorithm will help to pick which one receive the highest weight. Okay, so the researcher basically cannot decide I want to use which state as the control group or not. Okay, but there are some advantage of the synthetic control method. The first is we can conduct the very small sample analysis. So even if just one sample gets treated, so basically you can conduct the causal effect for a specific unit. So kind of individual treatment effect. Okay, and you can also conduct several heterogeneity analysis if you have more than one unit get a treatment. And you can, based on their characteristics, to conduct for each unit, based on their characteristics to conduct heterogeneity analysis. Okay. But there are some costs when you do synthetic control. First is their statistical inference. Actually, no one haven't derived the formula, the asymptotic theory for the synthetic control estimates. So that means we don't know this estimate, the gap here. We just know the gap, the point estimate for this gap, the treatment effect. But we don't know their standard error. We don't have formula to. No one know what this estimator is the asymptotic distribution. So we don't know the standard error and the distribution, so we cannot know, we have no theory to say about what's the p-value for this estimate. So the thing we can do is we use the data to generate the empirical distribution. And how can we do that? I will discuss later. That's so-called permutation method, which is also quite popular in the social science. Use that. If someone cannot derive the asymptotic theory for a specific estimator, we just use data to create the empirical distribution. And compare with this distribution with our estimate, we still can get some kind like the p-value, the empirical p-value, and can help us to understand whether this estimator is significantly from 0 or not. But that's the drawback. If someone can derive this formula, that will make very huge contribution to this literature. And also, the key education assumption is somewhat not obvious. It's a bit ambiguous. Because not like the difference is based on common trend assumption. Here, you don't need the common trend assumption. Whatever data set, you might find this weight. So we don't know whether we should trust this procedure, because there's no really have any assumption you need. You should be able to find some way to make it. Yeah. So there's not really have any restriction on this method. And computational time are quite far exist to the difference estimator, because you can know, you try to find the weight from this control group, but if the sample here is just 50 states and 1 treated unit, but so it's hard to apply such method to the individual level data or firm level data. If you have, for example, 200 individual get treatment, and for each individual, you also need to find from like 2,000 control group to find a weight for each 2,000 to each individual in this 2,000 control group to assign each weight for these people. It take long time and need a lot of computational ability to get the weight. So far, this can only apply to the small number, a small sample analysis. But potentially, it can extend to the large sample analysis. Okay.
With all of these disadvantages, how can you know that the outcome the results are significant?
You mean this? Or without the statistical inference, the syntactic theory?
And you said also the key identification assumptions.
Yeah. No, basically no identification assumption in this method.
So how can you be sure that the results are what you wanted?
Good. That's a good question. Compared to this method, I'm trust the different methods compared to this, because sometimes it can help you to get some result, but I'm not sure whether this is true or not. Yeah, but they can do something the difference cannot do. Yeah. For example, if you just have one treated unit, different actually cannot really implement. Yeah. And also, if you do not have common trend, this you cannot use difference. And this method basically further can allow you to try to provide some estimate to let you know what maybe causal effects like this. But so I would say if you can do both difference and synthetic control method, maybe you can try to do both, try to verify whether their estimates are consistent or not. Yeah. But you can apply this method to a lot of situations, especially your outcomes at aggregate level. Yeah, sometimes it's hard to find a good control group for example, at country level. Yeah. So this method actually apply to a lot of country level analysis. Yeah. For example, one paper about the effect of Brexit. How does this affect the UK's economic growth? They use other OECD countries as a control group. But if you direct use all OECD countries as a control group, you cannot find common trend. So they use this synthetic control and find some weight average that can reproduce the growth path for the UK before the Brexit. And they actually find after Brexit, the UK's growth rate declined compared to the synthetic UK. That means the UK, if the UK did not pass this referendum, the Brexit vote. Yeah. So it's very popular now, but whether you think the result is true or not, I'm not really sure, because they have several things. Like, yeah, first their inference. No one actually. We still rely on the permutation method, but these methods, a lot of is also quite standard. So you can consider should be fine. Yeah. So any questions? Okay. So next, I again use the potential outcome framework to point out what kind of causal effect you can get using this method. Okay, so it's the same potential outcome framework. So I use the same example that's kind of like original synthetic control methods paper. It's actually published in the Statistics Journal, but Abadi is the public policy, is a political scientist, And these other two could be, I'm not sure, should be some economists. Oh, they're all political scientists. Sorry. They're all so 3 are political scientists. Very good political scientists. Yeah. So they thank you. So they consider the single traded unit with multiple non-traded units, and they evaluate the effect of anti-tobacco program in California implemented in 1988. Okay. So we use this example to go through the key concept of the synthetic control method. So in 1988, the California passed this law, and this law basically tried to try to reduce the cigarette consumption. So, for example, they increased the tax for cigarette by 0.25 US dollar per pack, and also try to encourage a lot of anti-smoking campaigns, and also implement some laws, try to make they should not to persuade that they should not smoke. So they want to know how does this policy affect cigarette consumption in California. Okay, so based on this background, so we will observe J units over the 1 to T periods. Okay, so within this J plus 1 units, suppose unit 1 are traded, so that is California, and other states are unaffected. So unit 2 to unit J plus 1 are unaffected. And the pre-treatment period is 1 to T0. And post-treatment period T0 plus 1 to T. So you can consider pre-treatment period is around 1970 to 1987. And post-treatment period is 1988 to 2000, for example. And our goal is try to measure the causal effect of the treatment on the treated unit 1. Okay. Only for the causal effect, only for the California. So the treatment, the D is equal to 1, means these units get the treatment during the post-treatment period. And D equal to 0 means the units are always untreated, are not affected by the policy. Okay. And potential outcome Y1 is the outcome that the unit 1 at time t receive the treatment. So here we have the dimension time. So unit 1 received the treatment at a specific time. So during the T0 plus 1 to time t, the potential outcome with treatment will be realized. And Y0 is the potential outcome without the treatment, if there's do not receive the treatment. Okay. So note that the unit in synthetic control usually at aggregate level. Okay. But its potential it can extend to the individual level, but it's just hard to do that due to the computation issue. So observed outcome YIT is the observed outcome for the unit I at time t. And for the observed outcome before the treatment happened, Y0 will be realized for both treatment group and control group. And for the observed outcome after the treatment happened, T0 plus 1 period. It depends on whether you get a treatment or not. If you get treatment, Y1 realized. If not, Y0 realized. Okay. So the goal is we want to know the unit 1's, how does the policy affect the California? How does the treatment affect the unit 1? And we want to know the causal effect of the treatment over time for each year after the policy happened. We want to know the effect of policy on cigarette consumption in 1989, 1990 to 2000, for example. So each year will have the effect we call alpha 1. So it depends on which year you will have alpha 1 t plus 1 or alpha 1 with t. So every year we want to evaluate its effect. Okay. And so this alpha 1 is a vector for all these effects. Okay. So ideally, if we can observe y0 for each year, we can just compare with the observed outcome with this y0. We can get a causal effect of the anti-tobacco policy on the California's cigarette consumption. But the problem is this y0 we cannot observe because we never know what if the California does not pass this law. So we need to use some way to construct the y0. Okay. So the synthetic control method suggests how can we construct this y0 is we can just use the weighting average of the observed outcome from other state, from the unit 2 to unit j plus 1. Okay. But we do not use the simple average. So the difference basically is just use simple average. But here we assign higher weight for the states that are more similar to California. Their cigarette consumption are very similar to California before treatment happened. So that kind of state we will assign higher weight. And some states maybe their cigarette consumption trends are very strange, very different from California. Such state will just receive 0. Okay. So we will try to choose the weight for each state, and this weight, how we choose that is try to minimize the difference in the pre-treatment characteristics, including outcome and other covariates. Try to minimize the difference between the treated and the weighted, between the non-treated units. And if this minimization, we choose the weight, try to minimize this difference. Okay. So the weight, we use that to construct the synthetic units is the weighting that can minimize this difference. Okay. So if we can find such weight, that can help you to create a synthetic control unit. But sometimes we cannot find such weight because maybe the control groups are too different from the treatment group. No one really similar to the treated unit. So in that case, you still cannot use synthetic control method. It's possible. It's possible. Doing that, you still cannot get something like this. Maybe you get very different. It's still possible. So in that case, you might not be able to use this method.
Can you test it?
No formal test. You don't know. Yeah, that's a good question. You don't know whether, for example, this still has some difference, right? Whether this is good or not, no judgment. So that's why there's still some improvement in this method, not really formalized. Yeah. At least I don't know. Maybe some political scientists there are some. Yeah. To my knowledge, I haven't seen any formal test to see which is good match or which is not. Okay. So just use try to persuade readers to use, say, looks similar. Yeah. Okay. So the potential outcome in the synthetic control is kind of like assumed like this. They still have some assumption, but it's not very important. Not very important. They kind of like assume the y0, the potential outcome without treatment, is determined by this formula. these four components. One is the delta t, is kind of like common time effect, and you can consider it's kind of like the year fixed effect. And z is the observed pretreatment covariance, and mu I is permanent unobserved variables. Okay, and that's something we want to match. And it's kind of assume this unobserved variable has some time varying effects on the potential outcome. And epsilon is kind of like arrow term with zero means. So the problem for a synthetic control method is we actually allow very flexible unobserved effects over time. So this is unobserved factors over time can affect the potential outcomes change. And that is a key issue for synthetic control. Okay. The thing is we want to match this. Okay. But this is unobserved thing. Okay. So ideally, we want to find the weight. We want to match the unit 1. So we want to match the unit 1's. It's y0. We want to match this one. Because the things we don't know why unit 1's if they do not get a treatment. So we want to match unit 1's y0, get the recover the unit 1's y0. The potential outcome if the unit 1, if the California does not implement that policy. Okay. So based on this formula, we assume the y0 depends on this. We try to find the weight using the control group, try to match Z1 and also the mu1. Because if we match this one, basically we can match this just time. So we can match the y0. So we want to find a way to match these observed characteristics and these unobserved characteristics. Okay. But the problem is mu I is unobserved. So we cannot directly to choose the variable that can indicate mu I to match it. For the Zi is okay. Zi could be the population in California or the share of young people. That is the observed characteristics. We can find a weight from other states that can mimic, that can match these type variables. But for mu I, for example, could be the culture for the smoking or something we cannot use the data to measure. We cannot match this. So the beauty of synthetic control is the solution is we do not match the mu I, which is unobserved, but we can match something is observed. Is the data, the outcome before treatment happened. We try to find the weight that can reproduce the path of the outcome for the California before treatment happened. If we can find a way to match the outcome before treatment happened, so it's kind of like match the y0 1 1 y0 1 2 until y0 t0, because before treatment happened, y0 is observed, is realized. So it's kind of match the y0 before treatment happened. So if we can find such weight, it basically say we match the unobserved things. Otherwise, we cannot match y0 before treatment happened, right? Okay, so that's why in the synthetic control methods is we try to choose the weight that can help us to find the weight average for the observed characteristics that can match the California's observed characteristics, and also all the outcome before treatment happened for the California, all the time period.
subscript should be the subscript.
Subscript. Which one?
W.
Yeah, W.
That should be J, not I.
J. Oh, you mean J, right?
The W, J.
Yeah. Oh, thank you. Yeah. J, typo. Thank you. Yeah, it's J. Sorry. Yeah, I teach for a long time. No one actually tell me this. Yeah, this is J. Because this is J. Yeah, find the weight that can match this. So if you can match the outcomes passed before treatment happened, you can match this unobserved things. Because you directly, the idea is you directly match the outcome. If you can match this outcome for a long time, you should be able to kind of like catch the unobserved things, the change in these unobserved variables. Otherwise, you shouldn't match it. So here is the theorem called synthetic control estimation theorem. It's such say, suppose there exists the weight that can match the treated units in the pre-treatment period for the following variables. That is the outcome before treatment happened in each period. If we can find a weight from the control groups that can produce the average weighting average, that will be very similar to the treated unit 1, the treated unit in each time period before treatment happened. If we can find this, and also find the weight that can also match the Z. These weights are the same weight to match all these variables, all these outcome and observed characteristics. If there exists such weight, then the following claim will be true. That is, we can use this weight average for the time period after treatment happened. T0 is after treatment happened. The weight average of the outcome and the Y0, which we don't observe in our data, their difference will become 0, will be very close to a 0. That means we can use this to replace Y0, which is unobserved after the treatment happened. Because after treatment happened, unit 1, the potential outcome without treatment, we cannot observe. And this theory suggests that if we can find a way that can reproduce the outcome for the treated unit 1 before treatment happened for each time period, and also for their observed characteristics, then we can safely use this weighting average, this way create a weighting average outcome to represent the potential outcome without treatment for the treated unit 1, for the unit 1 after treatment happened. Okay. Their difference will be very small. Okay. And this under some condition. One condition is T0 need to be long. T0 need to be go to infinity, but practically cannot be that. T0 is the period, the length of the pre-treatment period. Okay, so 1 to T0 is the pre-treatment period. So you need to have sufficient long time period before treatment happen to match each year they can reproduce the outcome for the treated unit. You need to do that for every year to match very well. To make sure you can claim like this. Okay.
But that's the W star always exists.
Always no. So this theory says suppose this exists. If this exists, that means match this well every year, match this observed characteristic well, then the following thing will be true. You can use this weighting average to replace this unobserved potential outcome without treatment for the treated one after the treatment happened. So basically, and the condition also needs the time, the pre-treatment period need to be sufficient long. So this means, so basically from the graph, sorry, not sure. For example, it basically say, if you can find a weight to construct the synthetic California to match the such long time period before treatment happened, then I can say this synthetic control unit can represent the Y0. Yeah, that's basically the theorem say. But it say, suppose we find such weight, but it's possible we cannot find the weight can match this very well. Yeah. And what is the good match or not? It's also no formal definition. Yeah. So any questions?
So how many pre-treatment years is enough?
Yeah, that's also no regulation. But the theorem say go to infinity. So as long as possible. So for that, but practice is not, no such thing happen. So for them they use 1970 to 1988. Yeah.
So like how little would be too little?
Too little, for me, I maybe I require at least above 10 data points. Yeah, I think it's better. If you just can match, for example, 1 or 2 or 3 years, it's not enough to, maybe the matching is just by chance. Yeah, not really represent anything. Yeah. Yeah, but there's no really have any theory or regulation on this issue. So that's why some people criticize this method. Yeah. Okay, any questions? But this theory still continues. So maybe in the future, they will have some form, maybe more formalize this issue, this setting. Okay. Okay. Okay, so the beauty of the synthetic control method is mu I is unobserved. We want to match some unobserved thing, but we use observed data. If we can match the pre-treatment outcome for a long time and the observed characteristic for a long time, it's sufficient to match the unobserved things. Okay, so intuition is if we can match the observed characteristics and the observed outcome before treatment happened for a long time, yeah. Only if we can match the unobserved factor and these observed factors. Otherwise, we cannot match this outcome. But the condition is it needs to match very well for a long time. So if you just match 1 year, 2 years, does not really guarantee you match catch the unobserved things, the training unobserved variables. Okay, so in this California example, their result looks like this. They match several predictor, the several observed characteristics, like the share of the young people or retail price. And you can compare with, if you just take simple average, the result is a bit different. But if the synthetic California is more similar. And also the outcome before treatment happened, they also pick 3 to demonstrate they actually match better if you use synthetic control method. if you just sample average, the result, the outcome are quite different. That's also shown in the graph. Okay. Okay, so as I said before, the large sample asymptotic theory actually is impossible. No one derived such theory for the C-section control estimator. So that means we don't know whether this estimate is significant different from 0 or not, based on asymptotic theory. Okay. So later I will discuss, so maybe we can have a break. 不知道，谢谢。你们之前有听过这个吗？
我大四的时候有听过，但老师就是稍微带过，就用1个小时讲过这个玩意。
哦，好，因为我用了不止1个小时。
没有，是老师教的很好。
好。
脸超红。不能摔，这是公文，这是实际。
这边你知道这个是什么意思吗？这个地方在讲的是，我宣称这个变数代表后面的路径，所以你这边其实你要把手机看的是要算这个叫
好像没有，
可能没有，
但是因为我知道老师的都是以打为档，然后你后来写一下，所以那这个是你的档吗？
但基本上其实就是你这边要改成对，这个是 data 里面有一个叫做 global 的，就是宣告这个变数是在跑 data 的时候，它都会记得 raw data 代表后面这一串。
但是我的 raw data 放，就这样放啊？
就这样放，就是你资料如果摆在这边的话，你就 raw data 代表这个，那你到时候就只要用 raw data 这个词，就代表这一串。那也就是说然后只是你前面要加个几字哈的前字啊，也就是说这个东西 equivalent to 这个东西，你也可以不用这样弄，不过我是蛮建议的，因为你这样子以后改了，这等于跟这样子。
就像我的 Excel 档，我的
你也可以这样子，因为这个 raw data 就代表整串字啊，它就代表划一个东西这样。
不用打入写的，好像影片里面是 import position， 然后 using， 然后
要 using。可是
你的那个读稿那个里面好像没有，因为我是叫。但是因为你的影片里面是有 using， 可是我刚查你网络上那个读稿的好像没有 using。可是我想说是这样子，可是影片里面没有这一段，但是读稿里面有这一段。
我影片跟读稿不会完全一样。你有资料放在这里？
有。
你要先跑，宣告这个 raw data 是
I think I had to. 对。I
me que avanzaba y después de porque ya después de que después de mi
So then you have the
yo me quedé ahí el veo es como me veo como pero más de nuevo güey ya es ir no tocamos yo le puedo ir en directo porque se lo hace a mí me parece que es el segundo modelo. Pues eso dio algo de una montaña de pero no sé, no, pero bueno, I think pero es como que no felices o que creo que bueno, pero no This is just like
你尽量跟英文取名。
哦，好，那我再改。
会有一些问题，但是我觉得应该不是问题。
是啊，所以就他说他帮我，那就
question I have the exercises, like there's an age variable, and you generated a square. Right? So there's age and there's age squared, and then you use both of them in the regression. So I was just curious, like, what is the purpose of that?
Oh, let's just capture the age effect. Maybe the age, the relationship between the outcome and age is not linear. Maybe if you just put just age, this just linear. That means y and
it's just
a
straight line.
is a straight line.
Yeah.
So put h squared, another beta, h squared. It just allow maybe they have some nonlinear relationship. But it's possible this coefficient maybe is very small. So maybe it looks like still linear. Yeah.
And then
that's typical case we might control, especially income and age. Their relationship could be this. Yeah. When you become older, it also decrease.
And then one last question is like the homework one, we have to do like sum, duplicate, whatever. After we do that, do we have to use that one for homework 2? Like, so for example, homework 1, we have to create another column.
No, not necessary. Just practice.
But that's what for practice.
But if you also use the data set for your term paper, you can create the variable we really will use.
Okay.
Yeah.
So like for homework 1, we could just use any data set.
If you haven't decided.
Okay.
Yeah.
Okay. Cool. Thank you.
但是前面几页好像有些差，那这样它的
全部都是 J，
都是 J， G 的话是什么 G 的
不是 I 都是 J，I 其实都是 J。对。
那 G 哦，所以 G 的话是 J 吗？ G， 因为它是老师他这边的 G 是大，可是像因为那 G 的话，那 G 的部分是因为它这边 G 跟那个 G 的 I， 它这个 G 是的 I，
我可能把
那像这边的
这边我再重改的放一个小圈，在一个。
我不知道到底这里。
哦，对对对对。
这边也是，这边是个记的上，
这个阳面，因为它只会所有的关系啊，
这个记也是。
这个记是代表。
这边的记它
其实我觉得那个没有，
因为我们
知道说
就要去
增加
那所以然后就是
所有的一些论文，它最后的 outcome
你说其他的
还是有可能，不然他这样写，他到底有什么？
要去它是或者是他看的就这个
哦，但他一开始先写的一句话，
我知道了，
就说一定会，
全部都要
而且一定会发生，然后这到底是哪一方面的？这个有时候只是他们在写作的一个，因为他看的是严重犯罪，
这就 YYI1。
所以他当然要强调说，
因为这是
就是他是从 J
对，它是会
上升，帮他上升，对，通常是这样写，如果大家也可以自己去想，
那每一个州那个弯还是在一个州的。
我自己觉得那种合法化，我不太确定他到底会去哪里。为什么？对，可是我是排除掉大麻买卖的交易，那别种犯罪也不知道为什么。之类的，或者不用黑丝奶奶，他们也不会黑哦，对啊，你可以想这个比较有趣的类型，那大理还是这个很水，然后再看，那个是要那个 CR，然后我是觉得可能可以，假设你是挑某一个州最近的 test， 然后其他州在你的时间中，你有一个文章也是，但他看不是大楼，他看的是基这个到基础法化，怎么影响到那个但他还看，有点像这个样子。它是一个它也是用 state control。我忘记是哪个。我已经找到一个地方，他是帮他 review
Okay, so as I said before, the formal statistical inference for synthetic control estimates still not exist. No one haven't really arrived to know this estimator its distribution, their standard error. So we cannot use asymptotic theory, central limit theorem, to know what this estimates its p-value. So instead, we use the permutation method for the inference. So you can consider later you will see it's kind of like use the data or control group to generate the empirical distribution. The estimate is distribution, and we compare our real estimate with these estimates to see whether our estimate is sufficiently large than other estimates. So the main idea is how often we obtain the result of this magnitude, the California estimate. So basically say how often we obtain this big change if we just randomly choose another control group state and run the same synthetic control. When we compare with the California's estimate. And if we run a lot of such estimates, and we find many of them actually are all bigger than California's estimate, that might suggest this estimate maybe is not significantly different from zero, because we choose another state which do not implement any policy in 1988 in the control group and do the same synthetic control method. And we also find it that very big or even bigger estimate policy effect, but actually no policy happens. So that means maybe here we find it's not really sufficient large than this we randomly choose to get the estimate. So that's the main idea of the permutation method. Okay. So here I use the example to demonstrate how this works. So the step one is you implement the synthetic control method for each unit in the control group. So we have 40 states in control group. So for each state, we run the same synthetic control estimation and using other states as a control unit and do the same thing. And we will obtain a lot of estimate for each control groups. We also get the synthetic control estimate. And we compare with the real estimate in California. And we calculate how many the control groups estimate, the placebo estimate, placebo treatment effect, are bigger than California's one. And if they are bigger, we denote 1. If not, 0. And we calculate how many are bigger and divide by the number of the sample we have. And calculate how the share of the placebo estimate are bigger than the real estimate. And if this share is very big, that means many estimates actually are bigger than the California one. And then we might conclude this is not really represent the causal. It's just this finding just by chance. Okay. So the result will give us something looks like p-value. Okay. So if this number is very small, that means all the placebo estimates are smaller than the California's estimates. Then that means the California estimate for this change are kind of like outlier. It's not we can randomly generate such result, and then it can suggest this could be the causal effect of the policy. Okay. So what does this means is we get a California's estimate, and we want to know whether this is significant from 0 or not. We use other states, for example, Alabama, and run the same synthetic control. And for example, we don't get any difference. So we get their estimate. So that's the estimate here we have. So Alabama has this estimate. And obviously, Alabama's estimate is smaller than the California for every year. Okay. And you can do another state.
So, for example, for this state, the pre-treatment, actually, they do not match.
Now, yeah, that's a good question. Later we will go further. If the match quality compared with the California is too bad, we will eliminate such placebo estimate, because such estimates maybe after the reform their estimate may be bigger because they already in the beginning they did not match well. So we will not then include when we calculate the p-value.
Like an outlier difference or a huge difference, but I'm talking about even small difference should not be complete, because by the theory they have to perfectly match. Right?
No, yeah, but the problem is there is no theory say define what's the good match or perfect match.
But there's a condition for W, and the weight have to match, so that's such that why.
Yeah.
They have
The same, right? Yeah, the theory say they need to be the same, but theoretically practically cannot. So even for California, they still have some difference. And how difference will consider the good match? There's no formal definition.
So essentially, in practice, we try to find W, minimize the discrepancy.
Yeah.
Okay, only minimize it.
Only minimize. Okay. Yeah. And if they can be overlapped, become the same. That's much better. Yeah. So later you will see. We can exclude some control units that do not provide good match before treatment occurs, okay, during the pre-treatment period. So such we might exclude. And so the placebo estimate is you pick these 40 states and run the same synthetic control estimate and compare with each year their synthetic estimate with California's estimate. And if they are bigger, it will become 1. We want to know how the share of the placebo estimate are bigger than California. And this will give us the p-value. If this share is very large, that means most of the placebo estimates, which we just randomly pick from a control group, can be bigger than California. So that means these estimates is not really represent the causal effect, because for the other state they can also produce that. But in this example, actually not, because other state, if you run the same synthetic control, actually not many get a big change. Okay. But again, they do not match well also before. So here is just, so for kinetics, actually, they kind of like looks up a bigger thing. But they also do not match well. Okay. So sometimes you might find they do not match well, and you might need to eliminate such placebo estimate, because such placebo estimate maybe you should not consider include when you calculate the p-value. So for example, I use this graph to demonstrate such estimate might happen. So this just demonstrates the treatment effect. So this is the reform, and the starting line is California's effect. So why this is 0 is because this is the difference between the real California and synthetic California. The difference. So we draw this difference. So it's this. So solid line is this. So for California, after the reform, the effect is negative. Okay? And other gray line is 40 states, the placebo estimate. And you can see for example, these states, actually they do not match very well before the reform. So before reform, they should be very similar to the zero. As close to the zero as better. And some actually cannot produce that. So we can exclude this. We can exclude this. But there's no principle say how large we should exclude. You can just try. Okay? So some synthetic control fitting is bad. We shouldn't include that when we calculate the p-value. Okay? That might create, because such estimate, they might also have very big change after the reform. And that might make us to get a too high p-value. Okay. So how can we do that is we can adjust our p-value for the quality of pretreatment matching. So basically it's compare with the California's, the pretreatment period is root of mean square predict error, RMSP. So basically you can consider is this. We calculate the match quality, the predict California, the synthetic California and California, their difference, sum of the square. And every other state also do that. And we use the California's estimate as a benchmark. And we exclude, for example, some principle is we exclude like 5 times larger than California's predict error. Such placebo estimate we should exclude. Yeah. So, but there's no regulation say 3 times or 2 times or need to be the same as California. For example, if in this example, if you require the predict error before treatment, it should be the same as California or smaller than California. I think you will exclude all the placebo estimates because all the control group cannot really match well before the treatment, actually. So in that case, maybe you just pick if there the predict error is 5 times than California's 1. For example, this one might be excluded. Okay. Then you can get it. For example, if you exclude impose such principle, you might just have 29 control groups, 29 states in the ring, because you exclude other things. Then you might use this to calculate p-value. So in that case, you will find the California is kind of like outlier. It's give you a most negative estimate compared to other placebo estimates. So in that case, you can consider the p-value is basically is 0 because no one bigger than California's estimate, at least in this period. In that period, maybe 2 states are bigger than California. So the p-value is 2 divided by 29. And it should be also smaller than the 5% or 10%. Yeah. So any questions for this? Okay. Okay, so sounds like very complicated, but all of them you can use theta and R to implement this. And for R, all the method we discussed so far, you can implement using R, but we will start to we'll start to upload the video for R this week. And I also finished the status video yesterday, so I will upload it maybe tonight or tomorrow. Okay. But so far we just focus on data example. So you can download the do file SCN from the website, the link. So link here. And the data you also need to download. So do file is the SCN. And data you find from the raw data is smoking CADTA.
So these two are the required for this practice. And you also need to install two packages. One is called Tzu-Ting, one is called Tzu-Runner. And I'll explain what is this. What does this package do? So Tzu-Ting is only for a single treated unit. Okay. So far we just focus on the number of the treated unit is just one. So Tzu-Ting, this package can do this. And it will help you to compute the weight, optimal weight, and do some covariate balance. And Tzu-Runner, so Tzu can just give you the point estimate. And Tzu-Runner can help you to run the placebo estimate. So that means you can calculate the p-value based on this placebo estimate to conduct the statistical inference automatically. And it potentially can also extend to the multiple treated units. And for this case, we will discuss later. That means the number of treated units is more than 2. Okay. And Tzu-Runner, this package is based on the Tzu package. So they kind of like help each other. So they do different things.
Okay. So you can install by using this command. So you can open the do file. So you can install. Okay, if you have any problem, just let me know and open the data. So the data is the secret consumption. So it's the state level data and panel data for from 1970 to 2000 to 2000. And each state, Alabama, Alaska, and the outcome is secret consumption, secret sale. And others just the covariates. You try to match the income, beer consumption, share of the young people, and retail price. Okay. And the first step is you need to let data know this is the panel data. So when you open the data set, then you need to use T set to let data know the data is follow the same state over time. So first define is the panel variable. That is, you follow this unit, every state, not every household, not every individual, every state, this variable. And second is the time variable. So after that, tells data this is the panel data. And what is the panel variable, what is the time variable. So after that, data will know what's the unit number and what's the time period. We will use this information to implement our synthetic control method. So that's very important. So you need to say do that, and it will generate, let know this panel variables, state and time variable. Okay. And second step is synthetic control estimation. So think and put the outcome and the predictor, that is the covariates or the outcome you want to match. And you also need to let data know what is the treated units. So that's why you need to claim the panel data, because this treated unit, you need to put some number. That is the state. For example, in our data, it's a state ID. So in this, what does this mean is, for example, in our state data is 3. 3 means California. So you put 3 here is because it represents California. And this is because our data set say California is 3. California is 3. And White's data will know 3 is California, is because you say state variable is your panel variable. So you need to claim this, otherwise, which variable is the panel variable? Otherwise, Stata doesn't know. The number I follow is from using this variable, other variable. Okay. So California in the data set is 3. Okay.
And second, you need to let Stata know when is the treatment happen. So this is treat period. So this is treat unit. So 3 is California, and this is 1989 or 1988. 1989. Yeah, 1989. After 1989, the treatment happened. Okay. So the example is here. So outcome is cigarette consumption, and you put several covariates or so-called predictor you want to match. For example, you match the beer consumption. And here you have several options you can do. For example, you just want to match the average beer consumption from 1984 to 1988. You don't want to match 1970 to 1988. So just pick these 4 years. And one means the increment. So this means 1984, 1985, 1986, 1988. You just take the average of the beer consumption. You match this beer consumption over this period. And if you do not specify anything after the variable, they just take the average over the entire pretreatment period. So that is, they just match the average income over 1970 to 1988. Okay, and you can also match specific year. For example, you match the cigarette consumption in 1988 and cigarette consumption 1980 or cigarette consumption 1975. So in practice, you should put every year for your outcome before treatment happens. But here, just save the space, put just three outcome, 3 pre-treatment outcome. But you can put every year's outcome before the treatment happens. Okay. And then they will try to match this year's outcome. Okay. So after you implement this, you will get a result. So I will implement this for you. And this is the result. Okay. So the result will show treated unit is California and control unit is this. And why you can show this is because you put the label. You have label here. But if you do not have label, it's just the number. Yeah. And this is the year, the pre-treatment year, and post-treatment, the pre-treatment period. Yeah. And they will also give you some number like RMSP before the treatment happened. That means the difference between the synthetic California and California, their difference, the outcomes difference before treatment happened. Okay. And they calculate this. So this number is small is better, or small is better. And there's the composition of the synthetic California. So you can see the synthetic California is consist by 30% of Colorado and Connecticut and 24% Nevada, something like this, and 36% of Utah. I don't know why, but the data generate this. They say using this weight can minimize the difference
in the pretreatment outcome and the observed characteristics. You just propose. You just propose here. This outcome. Okay. So if you change your predictor, you will get another synthetic California. So there's no guidance say what kind of variable you need to put here. Just put observed characteristics and pretreatment outcomes, basically. Yeah.
So in the machine learning lecture, remember there's said you have tried to obtain some set of value that can minimize the object function. And I wonder, state up here, what do they do? Because I match, but here is you are saying minimize, so I wonder what's the difference. In practice, how state that implement?
Still, the form, but I'm not really sure the formula, but the formula still is try to minimize this. Oops, right here. The distance.
You mean the slide 24? That's what it is.
Slide 24. Where is this? There's slide number. You mean this one?
Yeah, I think so.
Yeah.
Is that the bottom? Is that what it about? I mean.
Oh no, not minimize this. Minimize the difference between this and this and this and this.
Okay.
Choose the weight to minimize this difference.
I see.
So if you find the weight can minimize this, you get this.
I see. So there's a certain algorithm for
Yes. They have certain algorithm. Yeah. It's a optimization problem to solve this. Yeah.
Okay. So yeah, that's the weight. And also you will generate the data
like to show the treated unit and synthetic units, their predictor are similar. Actually, are quite similar. So in terms of the pre-treatment outcome and also other observed characteristics are very similar.
Okay. So that's also good signal. And then you can generate a graph. So you can put the figure, they will generate graph for you. But I also recommend you can draw the graph by yourself. And I will provide I will provide but I will not explain now. Provide the example. You can draw the graph by yourself. But here, if you put the graph, they will generate graph for you. So you will generate like this. So you will generate a graph, and you can save it. You can save it
using the graph export to save. But later I will let you know, they will generate some file that can help you to draw the graph by yourself.
Okay. But you can also use their graph. Okay.
And you can also choose, there are several options you can do. You can also choose the control group you want to include by put this command, the option. So that means you want to just use the state number 4 to state 30. You don't want to use all the states in the control group. Okay, so that's something you can do. And also there are several algorithms that can give you better fitting but take more time. You can put in the data here, or for example, all up or nest, that just give you better fitting. And the result you can save. So you can use this option called keep to save your result. And you save your result, the file's name becomes this.
And let me show what is the result they can save. Okay, so here. Oh, it takes some time. Oh, sorry, because I use let me change. Okay. So the result
Save in the SC result, you use keep, this option. They will keep the result and save to the file. And it will give you some useful result. For example, the weighting for each state. And also the this is just the synthetic California's synthetic California's number and the outcome, and also the California real outcome and the year. So that's something you can use for your purpose. So for example, you want to know the weights, you can look at this file.
Okay. That is this.
Okay, and finally, the final step is statistical inference. Whether your estimate is significantly from 0 or not. And here you need to go to using Sim runner to help you to do a lot of placebo tests. Then you can get the p-value. And here you also, very similar to the Sim, you put the outcome and the predictor. And also let data know what's the treated unit and what's the treatment, when the treatment happened. And also you can also save the result you get. Okay, like previously. And here later I will discuss
this. So if you run the Sim runner, it will take longer time because it need to take let me show that. Time variable. Okay.
So it takes long time because they need to run the synthetic control for 38 times for each control group state, and then compare with the California's estimate and get a p-value. And the result is this. This is the estimate. So the estimate here is the gap between the California and the synthetic California. And this could be the 1989, 1990, 91 until 2000. And they are all negative. But we don't know whether this is the significant from 0 or not. So we need to compare the p-value. And for the p-value, they provide two type p-value. One is the original p-value, directly give you, compare with the placebo estimate, the formula we just mentioned. Another is the standardized p-value. That is, they consider the matching quality during the pretreatment period. So basically, these p-value, they do not calculate like this. So original p-value is just example. Original p-value is just compare the placebo estimate and the California estimate or real estimate. But these could be, this placebo estimate, maybe they do not have very good RMSP, the predict error before the treatment happened. So the standardized p-value consider that. So they will divide. Oh, sorry. They will divide the predict error, the RMSP, divide the RMSP for the estimate. And if the RMSP is too large, then this number will become very small. So basically, if the matching quality before treatment happen is not very well, these estimates, we will give them smaller weight or just reduce their estimate. So for California, actually they match quite good. So their number will become larger. Okay. So standardized p-value is try to take into account the matching quality before treatment happens. So I will more trust standardized p-values, these estimates. Okay. So for this estimate, you can see they are all significant. So p-value very small. Okay. Okay. So fine. Okay.
So when doing the synthetic control, how do you pick the variables? Like, is it?
Oh, that's a good question. No guidance.
Oh yeah.
You put the variable you think might relate to your control, the outcome.
But like for example, like 6 sale 1988 instead of 6 sale 1987.
Yeah, no. But I think for the outcome, you should put all. You can put all the every year outcome before treatment happens.
Oh.
Yeah. Because the goal is try to match this, the Y, right, every year. But here they kind of just put 3, and they actually match quite good. The result is like not this. Is this? Is I just generate. Is this? So this just match 3 years, some several years. So if you match every year, you can get better. You can get better. So the principle is you match all the pretreatment outcomes plus some observed characteristics. Okay. So that's answer your question.
But what if like there's a variable that like omitted variable bias?
Yeah. They are totally different methodology.
Oh.
There's you mean how can you know?
Or like how can you make the best fit? I mean, like how do you know what if like you're missing one variable that
What will happen?
actually never mind.
That's the here is their this graph is in their papers. They match better than the previous graph because they use all the pretreatment outcomes. Yeah. Just this match well is
the goal. Yeah. Yeah.
So you just have to try different things.
Yeah. So that's, I think this method does not really formalize. Means you can get very different results. Yeah. Okay. Any questions?
There doesn't exist a formula that we can calculate most likely to the base symmetric contribute.
Base
we can have我没办法有公式让我们直接知道说哪个是最合成的最像的。
No, because we don't know, we cannot globally search that because too many combinations and no formula can prove which one is the best. So it's kind of like data. So if the method is data driven, basically is you have a lot of manipulation you can try. Yeah. So any questions? Yeah. Okay. So another things you can do is you can use this option to eliminate the placebo estimate that has too big predict error. And you can put number here. So for example, if you put 5 here, that means you want to exclude the placebo estimate that has 5 times RMSP as the treated unit. So that means you want to eliminate the placebo estimate that has the RMSP 5 times larger than the treated units. Okay. So you can put 3 or 1. If 1 means you eliminate the RMSP as similar as the treated units. Okay. But sometimes if you too restrict, for example, 1 is quite restrict, you basically might exclude all the placebo estimates. It's possible. Okay, so that's the result here. Okay, so finally is you can also use keep option when you run the sim runner. They will also save the data set that can help you to do further analysis. So we will show what is the data you can get. Okay, so we just run it. Oh no. Okay. So you also take some time run the placebo test. Okay, so it will save the data to this file, the result. So I will just open this result. So the result actually store each placebo estimate, their result. So for example, it's the California, the pre-treatment RMSP, the predict error, and the post-treatment RMSP. Okay, and you can see the post-treatment RMSP for California is very large, and that's quite it's consistent with the graph because the graph shows after treatment, the synthetic unit and the California are very different. And they also show other states RMSPE, like Alabama, pre-treatment and post-treatment. So you can use this file to provide the pre-treatment RMSPE to exclude based on the California's RMSPE, to exclude the state placebo estimate that does not match well before the treatment happens. So for example, you just exclude the RMSP bigger than 1.94 times 5. If you want to exclude the placebo estimate that has too large RMSP. So in that case, you might exclude some states. So this record every state's RMSPE and also treatment effect. So for California, that's the effect we want to focus on. And for the other states, they also have the effect. This is just placebo estimate. So this file basically store all the placebo estimates and the result for the California and also other states. So you can use that to draw stable graph for your analysis. For example, if you have this data, you can draw the graph like this because you already get the treatment effect for California, so you can draw. And other states, you also have the effect, that's placebo effect, so you can draw this. And also you can use RMSPE to exclude the placebo estimate that does not match very well. Using this, like you can just keep only the pre-RMSPE smaller than the California's RMSPE, but the 5 times of the smaller than 5 times RMSPE as the California one. Then you might get the better graph. Some placebo estimate can be eliminated by when you do that. Okay, so that's basically the data example. And how you can also use R to implement this, but I will discuss when we teach R. So the next, I would like to use the example to let you know how can you use synthetic control method to answer very important questions. So we will discuss later.
So Professor, if you read a paper that uses synthetic control, how would you perceive it?
How? You mean
like would you think, oh, this synthetic control is still not very, I don't know.
Not very solid?
Yeah, solid. So would you like kind of not discredit it, but like kind of not like give it much weight?
Yeah, that's a good question. Compared to difference or regression discounting design the other methods, yeah, I will a bit suspicious of the synthetic control.
Okay.
Because you can see, they can do whatever.
Yeah.
They really, but some question, for example, the example we will mention later, only can use synthetic control. Yeah. Because synthetic control can use the data that not really good, like aggregate level data. Yeah. They don't need the individual level data. And also, just one unit get treated, you can evaluate the causal effect for this, for them. Yeah. So can apply to a lot of situations. Yeah. So at least they can give you some estimate.
Okay.
Yeah. So not bad, right?
就是外到外
高手率要好的，
都一样，
对，有一点。
但是那个是那个 C 人说的，那个 C 人说这样子会，就像那个有点像那个 T 零要 go infinity 一样，它在实际都不会真的达成。
对，但是
他只是说，
但是我不会 curious 到这个情如果成立的时候，后面做的东西。
是，所以你问那个问题是蛮重要的问题，就是说到底这个 match 要多不好，我们接下来这个都不能相信，都不能。
你感觉上，我感觉上，你把 next 再看说会跟它是我在怎么看，会让你在这种就是不太一样，很有把握的感觉。
但是好像来自于不太一样的地方，是 propensity matching， 它来自于它这个假设的问题，它就跟一般 regression 的问题就是很像，就是它没有办法完全解决 self selection 的问题。那实验好像为什么感觉是它一个它那个可以操作空间还蛮多的，就是你放不同的变数就不同的这个结果，然后你也不知道你现在做出来的结果是不是最好的？对，就是你找到最好的那个 counterfactual。其实你没有 globally 知道这件事情，因为它就是在 try 这样而已。
我刚好真的是第三个。哦。那时候
或者让对，以阿巴里比较出名，比较清楚。哦。
然后后面的话就是
但他是在 public policy，
我才胖。
一个阿巴里，
房间宝贝大部分永远都是瘦的。
对。
然后他是在他的房间门口贴他的体重。就是他房间门口放那个，他刚放上去我就看到了，这是他跟他两个人的然后我就吃下去的时候，我就偷看一下，然后他隔天吃什么就说，才收一期功课就躺回来了。然后说你有在看吗？我说对啊，我都会偷偷绕去看，没听到我都知道。
我被叫演员是最可爱的。
我看不出来了，真的看不出来那个体重，然后他会是那应该还好。
对，如果你固定你放的那个 predictor，
然后我这样开始
你要说
减肥，我就减肥干减肥大概看到就是他不会说，我说大概是增肌减脂。
对。
那你说你会有导致说
对。
他把那个开始，我刚才让我量一下。
是，可是你放的那些变数无穷尽的多。比如说我今天多放了一个执行的位置，多放了这个变数是很多种，这个是很多种。
应该有人蛮令人惊讶的，因为我不行。我不行啊，我不断，
就是因为高
是没错，高应该这个假象。我不想要高，
对，你说跟拉手用东西结合，对，什么有创意的做法？我不太清楚，搞不好也有人这样想，就说到底那些 predictor 那些 z 或者要怎么学？
你知道，
可是这个好像不太一样，因为它那个地方是它有个 penalty， 它之所以这样做是因为那个 penalty， 所以它有这边没有。
但是我就是有他偷
那个比较
然后
是
我们会有，
比较
我们是3个人，3个人吧。然后就是他每天都上去，然后我们也每天都上去，看有没有瘦。他每天上去，哎，就很胖。因为是我就很感激的，然后。
抱歉，我刚好是中校，我刚好是中校同事。
我是对女生的烦恼，是跟蛮有趣的。
女生烦恼不是这几个吗？
他那时候就是很快，他有痘痘也会
对，就是 Y 跟 W，Y 的 distance，Y 跟 W
你知道我长痘痘啊，一样，然后连
对
还有
对，然后 choose W，
因为他亮亮啊，我热到喘了，
这个就有可能，他把去放这边可以调整，不一定是这个。应该是 square，这个我也不太确定，因为我刚后面还有些什么说避得更好的，他应该是用另外一个 objective function。
都没有在看，都没有认真看。
我以为你们是私校的。
哦，没有，他在那个群组。
有空就去吧。
我问这个我们想要给他，就是他都想去，然后其实我们有正大的，然后正大的，然后有那你不可以乱讲。你上次我们去洗，可以给人讲。
好啦，对不起呢。
真可爱。
爸爸怎么办啊？我还没上啊。这样干嘛？
好，没事啊，没事。
干，男女平等好吗？
男女反正不平等性。
对，我们男女有年纪有问题。年纪有问题。
差不多。
对，因为我也是直接用 C
差不多。
其实这个就是直接要写扣
快说了，
他直接看他那个原始的那个，对，但应该就是在那边会告诉你。
我可以当干事，如果给我死。
那我可以当10个人。
我每天要去自己
做一次，对。
哦，我妈很会啊。
没有，他们做不太一样的工作。Sing 的话产生那个，
就是我听到那个菜单。
但是 Sing Runner 它其实是用 Sing 的东西，只是跑了所有的 placebo， 它可以帮助你做出 p-value。
因为太阳回去。
哇，我没有在跟他讲说我们要。我妈有一阵子，我妈有在我高中的时候，很认真的帮我做考试。我妈没有上班，我真的不很难。
让真的很累。
对啊，我也跟她讲可以这么做，但是她很。
哦，我知道你的意思，知道，
我记得她大概做了，她那时候的确大概做了1个月，然后后来不做别的事。
没有吗？后面有12个是每一年的，
对啊，就12款。
对，Sing 也有，Sing 也是每一年的都有。对，都有。
白目。
那你也许好奇是要不要变 average，就是把一般段
就是把那个
那 Sing Runner 它多做就是多跑一些，然后跟实际的估计，每一年去。没有，它其实就是应该是 Sing Runner 的作者非常 Sing， 然后他只是多跑了好几次这个 Sing， 然后得出每一个其他38个州的 synthetic control 的这个估计。就是多跑了38次的
去射多刷视频。
对，他这边用的是38个 stage。我不知道为什么他不用50个 stage， 但是他就是主要他的非常是38个 stage。
每一个都挑一个出来当缺点，然后剩下当做包含群。对，性没有。应该是性只是一开始。对，所以结论是，其实你可以全部用性方的，你可以用性方，但是性它还有多一些东西啊，直接帮你产出，但是那些图其实都可以自己画，然后拿一个桥用考完就考。没有，这些题都很好。
快下课之后，就是其他班会比较早下课。
我们蛮多就是要去工作。对，你也没有今年有几关，他是做资料有一些本来想去，我很想去做，可以读24小时。我的今年有些做，
我觉得会越看，
因为我在做，
我还把上学期的课本看出来，好吧？
我其实有
我现在要搞不懂的，有些模型真的搞不懂。
大学玩3年级，他能有学，他也就
听个兴趣。帮我写，对，感觉要模是什么东西？拍一个图，他的超想去看。
如果有
对，
像我今年几个学长，其他就要去学，不是去年，就是要去，对，就是要去工作。
管得这么多学生啊，不玩吗？没有啊。
我现在是用这种方式去找，我觉得也许就是那个我去知道学号的规则，所以我可以然后直接寄到就不用透过他们的
开始面试就是要查的正常一点，好好讲话。
我会给你那个 mail， 然后我也有做政治系，因为有时候政治系的也会想做这种量化的，他也会到这些系的。对啊，我 create 一些不错的学长，
他这有用吗？我以为他这有。
清华的我还在了解他的规则，反正我做一个清华我就知道。其实这个蛮好，因为我以前都是发很多资料，我是就是人高，有时候招来的就是很学术导向，可是如果你锁定就是挺大的，而且他们可能根本不会去上，
但是我在上面清华应该比较多。
你锁定反而会直接 approach 他，然后我最近送出去之后还有一些 feedback， 所以我再给你，反正我已经有，而且这蛮好建，就是说你就建，然后用 Excel 就是直接起来从0加到10，
low key
然后
in
序号，
between.
好像序号
Like
反正
Photoshop.
你大概抓它大概
Because
每
it
年收
also
100
has
个人。
different layers and masking with different brushes, and you can have like a selection and
不是学号是因为我清楚有个学号，还没有开始到，但学号展大概会知道，因为台大可能什么对对
And
对。
I added the career thing. And then I used one
是有规则，就是通常就是你的几个等级学加上，比如说
So what
像
I
菜
did
鸟，
was
它
I
水加
took his photo because his
好，
photo was
是是是，所以是我觉得我分享给你。
Okay, so let's continue. Okay, so synthetic control method actually can answer very important question in very timely manner. For example, this paper actually is published in the PNAS, Proceeding of National Academy of Science, something like this. It's a very good journal, and they are econ professor actually. This is econ professor, I think, and they try to understand how does the effect of the facing mask affect COVID case. Okay, they conduct this in the early in the 2020. So the effectiveness of facing mask in Western countries still debate, but I think now they understand face mask is really useful and is low cost and can really reduce the COVID case. But at that time, actually, not many people really think face mask is really effective. And this paper show that the face mask actually can provide can reduce the COVID cases quite a lot. And they use the synthetic control method. And without using a synthetic control method, I think it's hard to implement, to evaluate its effect. So many countries experience COVID spread. So until now is around like 2 years. And the effect of facing mask in the publics on the spread of the COVID has not been systematically analyzed at that time. Okay. So they use the Germans. They have choose some counties that can wear face masks. Require they have to wear the face mask in the public space in the very beginning, and they use this as an example, try to understand the effect of wearing the face mask or compulsory wearing the face mask on the COVID spread. So they focus on this case study, the Jena, this area. So this region was first region to introduce the face mask in public transportation and sales shop on April 6th. Okay. And by the April 29, 2020, all the German regions has to introduce the face mask. So everyone in the German regions, they need to wear the face mask in the public transportation and sales shops after the April 29th. So before the April 29th, only several regions has to do that. And one is this region, Jena. Okay. And the author argued that Jena actually is the representative case for study the COVID development. Because when you use synthetic control method, maybe some reader might question why you just pick this treated unit, why you just focus on this area. And maybe this area does not really represent all the Germans' case. So you might need to argue it's quite representative. And the author provides some data or number to show
it can represent the German's COVID situation. For example, on April 5th, the accumulative number of the COVID cases in China is per 100,000 people is 144, and the same number in the Germany is 155. Okay. So it's quite low, but it's beginning of the COVID. And the mean value of the COVID cases is for China is 126, and for Germany is 119. So it's very close. Okay. So they try to argue, study this area or understand the causal effect for this area can represent the effect for Germany. Okay.
Okay.
So the data they use is just the open data. The German statistics, they report the COVID cases. And also other observed characteristics are also from the open data. So a lot of synthetic control study actually does not require very high quality data or individual or household level data. You just can use open data and you can potentially answer some important questions like these studies. So they built the balance panel for around 401 regions, okay, in Germany. And the time sample period is 95 days. So from January 28th to May 1st. So the treatment happened in April 6th. Okay. So they between the January 28th to April 6th, they have sufficient long time periods. At least a lot of data points. Okay.
To that then can match the data. So the causal effect here we want to estimate is how does this face mask load affect the COVID spread. So we can only observe the China implement such policy, their COVID case, number of COVID case, Y1. We never know Y0 because we don't know what if the number of COVID will happen in China if they do not ask people to wear the face mask. So the counterfactual we need to construct is this, Y0. And the synthetic control method suggests we can just use other region in the Germany which haven't enforced people to wear the face mask to construct the weight average of their of the outcome to replace this counterfactual Y0. Okay. And if we can find a good weight, that is the weight for unit 1 to unit 401, try to find a way to minimize the difference in the pre-treatment periods, the characteristics and outcome between the treated units and non-treated units. Okay. And the weight requires the summations become 1. Okay.
Then we can use any difference after the treatment happened between the synthetic Jena and the real Jena. Their difference can represent the causal effect of the policy. So this is their result. So the solid line is the real data, and the dashed line is synthetic units. And you can see before treatment happened, they do not show all the time series from January 28th. So they match from January 28th to April 5th. Actually, before that, actually matched quite well. And after that, you can see the Jana's COVID case. This is accumulative COVID case. So that's they will continue to increase. But you can see after the policy implement, the growth is stopping. Okay. And if they do not implement such policy, the effect that means the average, the weighted average of control units, actually their COVID cases continue to increase. Okay, so this gap represents the effect of the policy on the COVID case. So actually reduce quite a lot, because you can see the original number is before the policy is around 150. And after that, actually, there's no increase. And if we do not have such policy, we might increase to 200 per 100,000 people. 200 cases per 100,000 people. So actually, kind of, it's reduced many cases. Okay. And then we can compare the synthetic units and real GENA. Synthetic GENA and real GENA. And they put two timing. One timing is they announce people has to wear the face mask. And one is introduction. That means they enforce people has to wear the face mask. And April 6th is introduction. They have to wear. Okay. So these they compare with their outcome actually before the treatment. They match quite well. All 129 for synthetic unit and GENA. And other like population density a bit different, but some other thing like female average age, and also physicians number of physicians also very similar. Okay, and also report the RMSPE pre-treatment RMSPE. Okay. So that's standard table you need to generate when you do synthetic control method. Okay. And also, you also need to report the weight for the your synthetic unit. So you can see the synthetic unit is consisted by just these six regions. Among the 400 regions, only these 6 regions receive the most, the majority of the weight. Okay. So others just 0. Okay. And also this just displayed the treatment effect compared with placebo effect. Okay. So you can see the effects here. They also do several robustness check, like they only use large CD or use specific CD. Okay, but that's something you can change, because for synthetic control method you can use different control group might give you different result. So you might need to do a lot of robustness check to persuade your readers. If you just change a little bit of your setting, does not give you totally different result. Okay. But if you change your setting dramatically, that of course might change all the result. But we don't require you have to do that. Okay. And you can see the results. This is show the p-value, adjusted p-value. That means they take into account the matching quality before treatment. Okay. And so you can see, after the policy, just around 14 days, actually the result is not significant. The p-value is around 0.2, so it's not significant. So after around 2 weeks, the results start to become significant. And that's actually consistent with some medical research, because after around 14 days, they might have some impact on the, because this maybe is just because before the treatment happened, they didn't wear the mask, so they actually get the COVID, but just the government haven't detected them. Okay, but after 14 days, all of these patients has already catched by the government. So after 14 days, the result becomes significant. I mean, it makes sense. Yeah. Okay. So they also do the subgroup analysis for by the age. Okay, and they find the most effective age group is for the old people. So for old people, due to this policy, actually save a lot of lives. Okay, reduce a lot of COVID cases. Okay, and they also do several placebo estimate, the several robustness check. That is, for example, you can do change your predictor. That you just use the predictor, the outcome before, like 1 day before the policy, or 7 days before the policy. You just use this outcome. You do not use the outcome very close to the policy, okay, to match, but they can match quite well. So even you use different predictors, they give you very similar counterfactual outcome. So that means their synthetic control estimate is quite stable. Okay. And they also do another setting, try to persuade their reader, this finding is not just by chance. It's not just by chance. So that's one technique you can use. They use so-called a placebo in time test. That is, they run the synthetic control method, synthetic control estimation, but they say March 26th is the treatment pattern. But actually nothing happened in March 26th. And they do the same synthetic control, but they use the outcome and the observed characteristic just before the March 26th. And they match before March 26th, but they find actually their synthetic estimate, synthetic units and the JNA, the real, actually still similar until April 5th. So after April 5th, these two lines start to become different. So that means something really happened after April 6th. Before that, nothing really changed before the policy. Okay. So that's another method, try to persuade reader you find that the timings really represent something. Okay, so this is their conclusion. They find the early introduction of face masks in China actually reduced the cumulative number of COVID cases by around 25% after 20 days. So after 20 days, these effects become emergence. Okay. And for the age 60 years old or above, their reduction is even larger. It's more than the 50%. Okay. So in overall, they find actually the wearing the face mask is very effective way to reduce the spread of the COVID cases, which we have already know now. Okay. So any questions?
So why not just use difference in difference? Why you have to use?
That's one thing is you can see the difference in difference might not have the good common trend before April 6th, because all these 400 regions actually are not very similar to the treated units, only these 6. So if you just use simple average of these 400, maybe the graph will not like this. Maybe it's very strange. But I'm not sure whether the author shows the graph for the simple average. But based on their result here, I think if just simple average, maybe you cannot find a good control group, because difference only do not have any requirement about only allow use simple average. Yeah. So any other questions? Okay.
So let's say one city was identical to Jena.
Okay.
Then would the weight just be one city?
Yeah. Do you mean it's possible?
No, it's not possible. Like hypothetically, if that were to happen, it would just only give what's one city.
Yeah.
And then at that point, you should just use difference.
Oh, you mean just use this?
No, if there was a city with just one.
Yeah.
Instead of, then at that point, you could just use difference in difference instead of.
Oh, you mean just use these two samples, two observation?
Yeah.
That's interesting.
Or isn't that what difference in difference is? Just using, like, I'm thinking about.
There's some. One thing is just technical issues. If your sample is very small, you cannot really do the hypothesis testing.
Oh, sorry. I was getting confused because the difference in difference class, you were showing two different states. Okay, so I was just getting confused. Okay.
No. The two different states, but we use 400 fast food stores.
Okay.
Yeah. So group, for different group, only two, but you have a lot of sample. Yeah.
So any questions? Okay. So synthetic control is quite useful. You can answer some interesting question, and you do not require to use very high quality data. Some aggregate level data is usually open data, and you can use for such studies. And potentially you can answer very big question like that. Okay. So far, we just focus on the number of treated unit is just one, and it's possible can extend to multiple. Okay. So the final thing I would like to address is if the number of treated units become more than 2, how can we implement synthetic control method? Okay. So if you have multiple